Hi everyone and welcome to our Advanced Microphone Measurement Seminar. Before we continue any further today, I'd like to turn things over to our friends at S&V Samford for a few words.
大家上午好，首先欢迎各位参加由 SV Samford 和雷士公司联合举办的 SoundCheck 麦克风测试进阶版的网络研讨会。今天的主讲嘉宾是雷士公司的 Steve Tatarinis 先生。研讨会大约会持续1个半小时的时间。为了确保会议的顺利进行，还请各位将自己的电脑麦克风设置为静音。在此期间，大家可以在聊天室以文字的形式进行提问，中文和英文都可以。请确认提问的信息发到了聊天室下方的起因组织者，也就是 Organizer Owner。我们的技术团队将你回答各个问题。问卷申请完成之后，便可以获得本次研讨会的电子版的档案。再次感谢大家的 Please go ahead.
Thanks guys, and thanks again for joining us today. I'm Steve Tatarinis. I'm the Technical Support Manager here at Listen Inc. So before we get going here, let's take a quick review of the topics that we're going to be covering today. And the first thing is we're going to demonstrate to you the standard microphone measurement sequences in SoundCheck. I know we talked a little bit about those in our introductory microphone seminar that we put on late last year, but this time we're going to take a little closer look at the sequences, and these would be for microphone substitution, equalize source, and transfer function. And while we're doing this, we're also going to talk about how to calibrate for these measurements, and we're also going to discuss what the trade-offs are between the 3 different measurement types. Next, we're going to move into some advanced measurements, and we're going to talk about polar plotting, self-noise and signal-to-noise measurements. We're going to do a demonstrative open-loop microphone measurements, and also active and passive noise rejection for microphones. Then we'll continue on with some MEMS microphone measurements. We're going to talk about microphone arrays and show you a demonstration of how to measure a mic array. We're going to talk a little bit about distortion today, specifically about intermodulation distortion, and distortion's a much larger topic. We'll be actually doing an entire seminar on distortion in the future. And we'll wrap things up with a few questions and answers that came in on your surveys from the previous microphone seminar, as well as answering some of the questions that came in today live. So let's start with the standard test methods. And there are 3 standard methods for microphone test in SoundCheck. And the first one is the substitution method, where we measure a known calibrated microphone, otherwise known as our reference microphone, and then we measure the unknown microphone that we want to characterize, otherwise known as the DUT microphone, the device under test. And then we can use some post-processing to calculate the DUT microphone response and sensitivity. So here's the mic substitution sequence, and you'll notice that when I open the sequence, we get a sequence note that opens with it, and this is pretty standard for a lot of the example sequences in SoundCheck. The sequence note gives you an introduction to the sequence, what to expect, a screenshot of what the final display might look like, recommended hardware, how to set up and calibrate the hardware, a schematic diagram of how to set the system up, a look at the sequence on paper, and at the end some suggestions for further sequence development. But now let's go back over to SoundCheck. Let's run the sequence. What we're going to be doing here is measuring our reference microphone, and then we're going to be replacing it with our DUT microphone, making another measurement, and then doing some post-processing to determine the actual response of the DUT microphone. So let's hit the start button, and then we'll look at the results and take a look at the sequence. So before we proceed, we just prompted to make sure that the microphone input's calibrated and to place it in front of the mouse simulator and press continue. So we've finished the acquisition with the reference mic, and now we're prompted to place the DUT mic in front of the mouse simulator. sure it's in the right position here. That looks good. And press enter. Okay, so here's our final display. We can see in the large XY graph up here at the top of the display, this is the normalized response of the DUT mic, and we can see that it's very flat relative to the reference microphone, so we can tell it's a good high-quality microphone. Down below here, we have the reference mic curve and the DUT mic curve, and we can see that from some post-processing that we've done in the sequence that the 1 kilohertz sensitivity of the DUT mic is minus 34.5 dB relative to 1 volt per Pascal. And if we open the sequence editor, we can take a look at what's going on in the sequence here. We have our stimulus editor here, which is set up to use the frequency stepped sweep from 10K to 100 hertz. We're using a very small output level of 10 millivolts RMS because we're actually feeding a direct out into the amplifier of the amp connect here. So we want to produce a very small level to account for the gain of the amplifier. So then moving back to the sequence here, we have 2 acquisition steps, one for the reference mic and then one for the DUT mic. And then we have a couple of analysis steps. And in the end, the curve division step here, where we're doing arithmetic, is giving us our normalized response curve, where operand A is the DUT mic fundamental and operand B is the reference mic fundamental. So once that step is applied, it gives us the normalized response that we see up on the large XY graph here. And the second post-processing step here is doing an average at 1 kilohertz of the normalized response to give us our 1 kilohertz sensitivity. So there's a look at the mic substitution sequence. Let's go back to our presentation and talk about the next method. And that's the transfer function method, and this is pretty interesting. It's similar to a substitution method, but we're not going to post-process the response curves. We're actually going to analyze the reference and the DUT waveforms. So once we've done our acquisition, the reference and the DUT recorded time waveforms are analyzed using a transfer function algorithm. And the transfer function is very flexible because it allows for the use of many different stimulus types. So we're not just tied down to using a step sine wave or a log sweep. We could use noise, we could use music, but in this case, we're going to use a multi-tone stimulus. That's one of the available stimulus options in SoundCheck. And the nice thing about multi-tone is that it allows us to create very, very short duration stimulus types that give us very accurate and very repeatable measurements. And in the case of the example sequence here, the stimulus duration is 1 second, and we're able to measure across a very wide range of frequencies in a very short amount of time. So let's run the sequence, take a look at the results, and then take a look at the sequence. Measured our reference mic, and now let's drop our DUT mic into the holder here and get that back into the reference position and continue. So here's our final display up on the large XY graph. Again, we have the normalized frequency response. We have the sensitivity displayed in the table here. And over here in the smaller XY graph, we have the auto spectrums of the stimulus and response waveforms. In this case, the response waveforms of the reference mic and the DUT microphone. And if we take a look at the sequence, we can see how we're actually doing the analysis here. So we have an acquisition step for the reference mic, another one for the DUT mic, and that's giving us these 2 waveforms in the memory list for the recorded time waveform, reference mic, recorded time waveform, DUT mic, and these are then being used in the multi-tone analysis step, which is essentially a transfer function type of algorithm. And we have the reference mic waveform being used as the stimulus and the dot mic waveform being used as the response waveform. I think other things of note here over on the frequency tab is that we're using a 12th octave analysis resolution here. We're using RMS scaling and complex averaging, so in case we wanted to get some phase information, it would be available to us. And we're producing the spectrums of the stimulus and the response, and we're also generating a frequency response function that we're displaying over here in the sequence. So there's a quick look at the transfer function method in SoundCheck. Let's go back over to our presentation slides and talk a little bit about the third method, which is the equalized source speaker method. So what we're going to do here is we're going to use the reference mic to equalize the source speaker. And there's a calibration sequence for that in SoundCheck that I'm going to demonstrate to you momentarily. And then once the mouth is equalized, we will use that to measure the dot mic. We're going to show you how to equalize and calibrate a reference speaker using SoundCheck. And to do that, we need to open our calibration editor, and on the output signal path, we'll be using the mouth sim output signal path for this measurement in this sequence. It's assigned to output hardware channel 3, which is our amp connect, and we're going to be saving all of our calibration information into the calibrated device file called B&K 4227 mouth, which is the model of mouth simulator that we are using here today. Down below in the calibration information section, we are telling SoundCheck that we want to use the reference mic for the input signal path, and that we want to use the speaker equalization calibration sequence. So now that all of this is configured, I can click on Calibrate Device, and I get a prompt here to make sure that the microphone input is calibrated, which it is. And it tells me I can locate the microphone up to 1 meter away from the source speaker, and I can press Enter to begin. So the first thing here is that I'm prompted for a test level, and the test level is very important because we want to make sure that our calibration level is the same as the level that we're going to be testing our microphone when we're using the sequence. Our source speaker probably isn't completely linear, so for that reason we don't want to calibrate it at 80 dB when we're going to be making our measurements at 94 dB. So today, like I said, our target is to test the microphone at 94 dB SPL, so I'll press Enter here. And you just heard a brief 1 kilohertz tone, and that is being used to calibrate the output sensitivity of our system here. So that includes the sensitivity of the internal sound card and the amp connect here, the amp connect amplifier, and the mouth. So it's that entire signal path that we're calibrating for sensitivity. And the next step is to tell SoundCheck the range that we want to equalize the source across. And in this case, we're going to accept the defaults, 100 hertz for the low frequency cutoff, and 10 kilohertz for the high frequency cutoff. And when I press Enter here, we're going to hear a sweep. SoundCheck is going to display a little information in a table and in a results window here. And next we should see a response curve. And this is the response of our mouth simulator, and it's been normalized to 0 dB at 1K. You can see that there are also some upper and lower limits on this graph. As long as the response of our source fits within these limits, we're good to go. The limits are actually plus or minus 20 dB, so any good source speaker is going to result in a passing verdict when it's passed through these limits. So we're good to go with the equalization process that's going to happen next. And what SoundCheck's going to do, it's going to take this mouth response curve, create a reciprocal, and then use that reciprocal as an equalization curve that will be applied to the stimulus when it's played back in the next part of the sequence. So after that happens, we'll see a response curve showing our first attempt at equalizing the response of the mouth. So there's our first attempt at EQing the speaker. It's not bad, but I know we can do better. So what this equalization sequence allows us to do is to make another attempt at equalizing the mouth simulator here. So I'm going to press enter to continue. I'm going to be asked if the response is flat enough, and it isn't. And if I click no, we're going to have another acquisition and analysis step and display the results of the second equalization attempt, which should be much flatter. And so there it is. It's much flatter than the first attempt. And I know from experience that in this particular measurement environment, it's probably not going to get much better than this because we have some reflective surfaces nearby. So I'm not going to try a third attempt. I don't think it's going to be any better than this. So if I press enter here, I'm going to say yes, the response is flat enough. And that completes the calibration of the mouth simulator. And we can see over here in the memory list on the curves tab, if we expand the calibration group, we can see our mouth equalization curve and also the mouth correction curve. And the correction curve is essentially all that leftover non-flatness at the end of the last equalization attempt. You can see that the y-axis scale here is pretty small. So this is a very small amount of correction that gets applied during analysis, and the equalization here is applied to the stimulus file before the acquisition step. And we also have some sensitivity data for the mouth as well. And there's our sensitivity, all saved to memory. Okay, so let's open the example sequence that uses the equalized source. And again, we get our sequence note, gives us a description of the sequence, an example of the final display, hardware requirements, how to set up and calibrate the hardware, system diagram, sequence logic, and suggestions for further sequence development. So here we have our stimulus step, and you can clearly see the effect of the EQ on the stimulus waveform up here. If I disable the EQ and update, and enable the EQ and update. So that's what our EQ curve is doing to our stimulus waveform. Before I run the sequence here, I'm going to remove the reference mic, and I'm going to take the dot microphone and place this back in the reference position above the mouth. Make sure that's in the right spot. And we're good to go. So press start, we'll look at the results and look at the sequence. So once again, we get a very flat response curve from the dot mic. It tells us that it's good quality microphone. Down below here, we've actually taken the fundamental and aligned it to 0 dB at 1K, and we're passing it through a set of limits that are plus or minus 3 dB. We pass those limits very easily. We're displaying the sensitivity in volts per Pascal down here in the results window, so 18.9 millivolts per Pascal, and the microphone response limits, we were well within the pass-fail limits applied to the frequency response curve. And just a quick look at the sequence itself. It's pretty straightforward. We have our stimulus step, acquisition, and analysis. We do a curve average step, once again, to find the average value of the fundamental at 1K, which we're calling sensitivity. And then we have our limits for sensitivity on the single value and the response limits on the response curve and our final display. So there's a quick look at the equalized source speaker method in SoundCheck. So now that we've demonstrated the three standard test methods, let's take a moment to discuss some of the trade-offs and other considerations. So all of these methods require that the source speaker be stable. So it should have a stable frequency response that doesn't change over time due to heat, humidity, other changes in environment. If your speaker isn't stable and you've calibrated and it starts to drift, then your measurement confidence is going to go down. So I think the point here, and that we'll keep reinforcing, is that a really high quality source speaker is the way to go when you're making microphone measurements. The equalized speaker method has the advantage of uniform level at all frequencies, but it can push the speaker harder and perhaps closer to instability if there are frequencies when lots of equalization are being applied. Substitution method, on the other hand, might allow for the source speaker to be used over a wider frequency range. Because we're not EQing it, we can just use an unequalized response to compare the reference mic and the DUT mic. The only consideration here is that at the low frequencies and very high frequencies where the speaker might be rolling off, we have to be careful that we're not measuring into the noise floor of the room. So just be aware of the environment that you're testing in with respect to upper and lower frequency limits when using the substitution method. A speaker that has a relatively flat response is preferred as opposed to one that has a lot of response peaks and dips. And really, lastly, microphone position is critical. It has to be stable in order to get accurate, repeatable results. A lot of manufacturers use very rigid fixturing that always guarantees that the microphone and the source speaker are going to be in the same place. Other people might use lasers to help precisely position the microphones and the source speaker. So whatever works for you, but there's a couple of the most typical approaches is having a very rigid fixture or using some sort of laser positioning. Our next topic is polar plots. So the intent of a polar plot measurement is to measure the directional response of a microphone. And we talked a lot about microphone types and microphone patterns in the previous webinar, so I hope you remember some of that. And in order to do this measurement, we're going to need a turntable, and we mount the microphone on a turntable and we rotate it in predetermined increments relative to a calibrated source speaker. And we start directly on the axis of the source speaker with a microphone pointed at it at 0 degrees. We start by measuring a reference mic at 0 degrees, and then we substitute that with the DUT mic. And we get three important results out of this sequence. We get the polar display, we get a directivity index, which is a curve, and a directivity factor, which is a value. And over here, we can see a little schematic of the setup diagram. We have our turntable. We have a DUT mic, a reference mic. We have possibly some sort of phantom power for our DUT mic. We have an audio interface and an amplifier for our loudspeaker. It would take quite a while to demonstrate one of these sequences in action to run it from start to finish. So what we're going to do today is just use some recall data and look at a couple of different microphone types and the types of results we might expect if we had actually measured one of those. One important consideration too in the setup of the turntable is that you want the acoustic center of the microphone to be aligned with the center of the turntable. So most microphones have on their turntable, or their platter, if you will, they have various mounting positions and bolts, so you can easily take your microphone stand, and in this case we're showing some sort of a boom stand, so we have some control over the height and location of the microphone relative to the center line. So any common turntable will allow you to have this type of bolt down so you can properly position the microphone. But it's really critical that the acoustic center of the mic be at the center of the turntable in order to get the proper measurements, and also on the center line of the source speaker. So very important to follow the setup instructions as shown here in this hardware setup. So here's our polar plot example sequence. It comes with a sequence note, and as you can see, this sequence is called Substitution Method using outline ET253D turntable. We also have a polar plotting microphone sequence available for the Linear X LT360, and you can find both of these sequences on the Listen website. Just like the other sequence notes we've looked at today, there's an introduction describing the sequence, what it does, a screenshot of the final display, the software requirements, the hardware requirements, and in this case, instructions for connecting the turntable to the SoundCheck host computer. This does communicate over a LAN, so it's a little more complicated in terms of the setup, but once it's set up, it works very reliably. This sequence also uses a custom step or a custom VI for communication from SoundCheck to the turntable in terms of controlling its positioning while the sequence is running. And then how to set up and calibrate your hardware, system diagram, sequence logic, and lastly, the suggestions for how you might further develop your sequence. So I'm not going to run the sequence right now, but what I'm going to do is recall some previously measured data, and that's a feature that's actually built into the sequence here. So when I press the start button, I'm asked if I'd like to recall some data, and I'm going to say yes. File open dialog's going to pop up here, and I'm going to select some data that we've captured from a cardioid microphone previously and load that into SoundCheck. So this is what our final display would look like after making a polar measurement. And we can see here that we have actually two polar displays, one for the low frequencies where we're plotting 125 hertz polar, 500 hertz, and 1000 hertz. And then down below here we have our high frequency polars at 2K, 4K, and 8 kilohertz. We have an aligned frequency response graph up here. We have our directivity index curve shown down here, and two tables, one showing directivity factor and one showing some sensitivity information of the microphone under test. Let's open up the sequence editor and take a quick look at what's going on in the sequence. There's a lot going on. I could probably spend the next 20 minutes going into great detail here, but I won't. I'm just going to give you a quick idea of what the theory is behind this sequence. So the first 13 or so steps here, what we're doing is we're making sure that the turntable has been returned to its 0 degree position before we start making any measurements. And at this point, we have a reference microphone mounted on the turntable in front of the source speaker, because this is actually going to be a substitution method test here. So we measure the reference microphone at 0 degrees. And then we have a couple of we have one acquisition step and a couple of analysis steps here. And what we're doing in analysis is, because we're using a continuous log sweep and time selective response analysis, we're making a measurement. We're looking at the impulse response of the first analysis, and we're looking for the first strong reflection in that impulse response. And then we're automatically going to take that first strong reflection where it occurs in time, and we're going to pass that value into the next and all of the subsequent analysis steps as the stop time for the TSR analysis. Once that's all done, the sequence enters a loop, would be prompted to replace the reference microphone with the dot microphone, and then we'll make a measurement of the dot mic at 10-degree increments. And every time we make a measurement, we'll be normalizing the response back to 0 degrees, back to the reference microphone, taking some sensitivity data. And then at the end of the loop, we'll be moving the turntable 10 degrees and repeating this. And we'll do that 18 times, which will give us half of our polar measurement. And then we'll essentially mirror that half of the polar to complete the measurement from 180 degrees out to 360 degrees. So that's a quick look at the microphone polar substitution using the outline turntable. Our next topic is self-noise, how to measure it. So the process is like this. First, we measure the equivalent input noise with the mic input shorted. And that's the current configuration of the amp connect here. And then we measure the microphone self-noise. So these are essentially two spectrum measurements. And then we display both the noise spectra plus the equivalent input noise and the self-noise values on the final display. And the important thing is to have the dot microphone mounted in an isolated enclosure like this B&K 4232 here, or inside of an anechoic chamber. But definitely one of the prerequisites here is to do this in a very quiet, controlled environment. So let's go back over to SoundCheck, and let's run our sequence. So this sequence gives you the ability to recall stored preamp measurements. So if you need to measure a series of microphones, there's no sense in measuring your preamp noise over and over again. So there's a nice little benefit to the sequence. But in this case, we'll click no, and we will actually remeasure the preamp. There is no gain on the preamp. There's 0 dB, so I'll click OK here. And I do have a 150 ohm load across the input at this point, so we'll click OK. And I will replace the microphone input noise file, and there's the input noise spectrum, or what would call the preamp equivalent input noise. So we'll press enter to continue, and it's going to prompt me to remove the shorting plug and to connect the microphone. So I'll just do that now so we can get the microphone warmed up before we make that measurement. I'll press enter, connect the mic under test to the power supply, and place the unit in an acoustically isolated enclosure, which it already is. So I'll press enter here. And there's the microphone self-noise. It's asking me if I'd like to enter the sensitivity value. Why not? And I'll do that in millivolts per Pascal. And it's 15.6. So this message tells me that my self-noise measurement is going to fail because the microphone self-noise isn't high enough above the preamp noise to ensure an accurate measurement. In this case, I could increase the dot mic signal path gain, or I could try to find a lower noise preamp. But let's continue on to the final display and take a look at the results from this measurement. So as you can see here, in the final display, we have the equivalent input noise in blue, and then the orange spectrum is actually the microphone self-noise. So down below, a certain level, it's starting to poke its head up above the noise floor, but generally it's pretty close to the noise floor. The other information that we'll display on the final display here is the preamp equivalent input noise, the microphone self-noise in dBV, and then the self-noise of the microphone expressed in dBSPL, and it's down to about 25 dBSPL. We also show the corrected waveform here, and we show some information about the waveform over in this table, the transient peak, where it occurs, and what's the actual crest factor. So if there's any severe transients, in the waveform, it's an indication that you might want to try to make another measurement or check out all your lines and cables because maybe there's some other interference there. So there's microphone self-noise, and we're going to continue into the next section here. Let me go back to my PowerPoint presentation, and moving right along, we're going to take that one step further, and now we're going to measure microphone signal to noise. And it's similar to what we just did, but we're going to add another component here where we're actually going to introduce some signal into the measurement so we can make a signal to noise measurement. So we measure the DUT mic self-noise, analyze that, and then a 1 kilohertz tone at 94 dB SPL. Then we calculate the A-weighted spectrum for both of these measurements, and we power sum the self-noise spectrum, and then we calculate the DUT sensitivity at 1K from the signal spectrum. And then from all of these spectra, we can calculate the DUT signal-to-noise ratio, equivalent noise level as well. And the equivalent noise level is the test level minus the DUT mic signal-to-noise. So let's run our sequence, and then we'll take a look at the results and the sequence. I don't have any preamp gain. I've connected the mic under test, and I have calibrated the source speaker. Probably won't hear any sort of stimulus because the box is pretty well isolated, so we'll have a bit of silence here while the sequence runs. And here's our final display. So if we take a look, we have a couple spectra here. We have the self-noise spectra, which is the orange curve, which is kind of buried underneath here. And then we have the signal spectrum, where we have the 1 kilohertz tone. So looking over here, it tells us that the DUT mic self-noise is about 95.2 dB down A-weighted. The DUT mic signal is at minus 36.1, so that yields a signal-to-noise ratio of 59.1. And then we also get the equivalent noise level of 34.9, which is the difference between the signal-to-noise and the actual signal itself. So there's a look at our measurements, and the sequence itself is pretty straightforward. We have a prompt to enter our test level. We have our 1 kilohertz stimulus. We're recalling some weighting curves and entering our preamp gain. Our first acquisition is record only, where we're just recording the microphone noise. We do a spectrum analysis on that and A-weight it, and any gain correction to compensate for whatever preamp gain that we're using. In this case, there wasn't any. And then we power sum the corrected and weighted curve. The next acquisition step is actually play and record, where we're playing back the 1 kilohertz tone. Again, we analyze that, take an average at 1K. Then we have another preamp gain correction and a calculation for the DUT signal-to-noise ratio and a weighting of the DUT mic signal, and then more correction. And we do a level conversion from Pascal to dB SPL and a final calculation for the equivalent noise level. So there's a quick look at our microphone signal-to-noise ratio sequence. Our next topic is open loop measurements. And open loop measurements are required when the DUT mic is embedded in a portable or standalone device where the signal can't easily be returned to the measurement system in a closed loop. So for instance, this tablet here, your cell phone, anything that has a microphone embedded in it. But if the device has the capability to record, then we're in luck because we can make a recording on the device and transfer that recording back to SoundCheck. So the procedure here, the process is that the stimulus is played through a calibrated source speaker. It's recorded on the portable device, and then the recorded waveform is transferred back to the SoundCheck computer for analysis. And here's a little schematic of how this might work. We have our recording device over here, our source speaker, and our amp connect. And so the signal comes out of the source speaker, recorded on the device, and then transferred somehow back to SoundCheck. Now, in order to do open loop testing, there's a number of post-processing steps required. Because the stimulus and the response waveforms may be at different sample rates, and that's actually the case in this particular measurement here. The tablet's going to be recording at 48K, and the amp connect is operating at 44.1K. So what's going to be required here is that the waveform that's coming in from the DUT should be resampled to match the stimulus. And to take that one step further, after we do the resampling, the waveform should also be frequency shifted to account for any remaining small sample rate errors, because there could be some slight differences in the clock speeds on the test system and on the device under test. So that's always a good habit to get into. Now, previous versions of SoundCheck before SoundCheck 18.1, which we're using today for all of our demos, required waveform windowing if the delay in the recorded time waveform was greater than 1 second. In other words, if there was a gap between the start of the recording and the actual presentation of the stimulus to the device under test. But there's a new feature in SoundCheck 18.1. It's called Auto Delay Plus, and it's delay agnostic, and it requires no waveform windowing, which really simplifies these open loop microphone sequences. In prior versions of SoundCheck, you had to do a lot of post-processing to find the start of the waveform, determine how long it was, where the end was, and then passing it through a windowing step to remove any excess delay at the beginning of the waveform. But don't have to do that anymore. So Auto Delay Plus is a real great benefit for people like me who are about to do an open loop microphone measurement. Okay, so let's run the sequence, and there'll be some prompts along the way. And at some point, I'm going to have to transfer the waveform from the tablet up to the cloud and down to the computer. So there'll be a little bit of time where we're just moving some files around. This recording program saves to Google Drive, so that's what I'm actually going to be using today. So I'm going to begin recording on the device. Press the record button. I'll let a little bit of time pass before I continue so we can have some lengthy delay at the start of the recording. And press enter to continue. And stop the recording and transfer the file to the computer, and the file must be in WAV format, which it is. And what I'm doing here is uploading the recorded time waveform from my tablet to Google Drive and then downloading it to my SoundCheck PC. Now I'll press enter to continue, and what it's going to do is prompt me to select the file that we just downloaded. My downloads folder, here we go. Press OK, and then at this point we'll bring the waveform into SoundCheck, we'll resample it, we'll frequency shift it, and then we'll do some analysis and display our results. And there we have it. Up here in the top XY graph, we have the microphone response. Down below is the recorded time waveform. A little bit of noise here before we actually presented the stimulus, but it didn't seem to create any issues with the analysis. Auto Delay Plus identified the recorded part of the waveform just fine, and we have a results window up here that shows us the calculated sensitivity at 1K. It's a little bit less than minus 20 dB RE1 full scale per volt. And let's just quickly take a look at the sequence itself. So there are some operator prompts in here, but really, we have an acquisition step that's just playing back the stimulus, and then the operator message to transfer the file to the computer. Once it's there, we have a recall step, and then we go through the resampling step, where we have our recorded time waveform. It comes in at 48K. We resample it down to 44.1, and then we take that resampled waveform and pass it through our frequency shift. So operand A is the recorded time waveform that's been resampled. Oops. And then our reference frequency comes from the stimulus waveform. Once we do that, it's just a simple matter of fundamental analysis, so we can get our fundamental curve, and then we do a curve average to derive the sensitivity. And there's a limit step there for sensitivity, and there's one for response that we're not actually showing the limits here on the graph, but that's baked into the sequence. So you can find an earlier version of this sequence in your SoundCheck install, and we'll be updating it in future versions of SoundCheck, so you can take advantage of the Auto Delay Plus feature. And that's a quick look at open loop microphone. So the next topic we're going to cover here is microphone noise rejection. And as you can see, we've brought in some additional hardware for this particular demonstration. So we've got our hats. We mounted a communications headset on it with a boom microphone. And we have a couple of small speakers on each side that we're going to use to generate a noise field around the hats and the microphones as part of this test. So the test characterizes the noise rejection capability of, in this case, a communications microphone. And we start by measuring the ambient noise spectrum in the room using the reference microphone. Next, a signal output, the speech, is played from the mouth simulator and recorded using our calibrated reference mic at the mouth reference point. Then we use a noise output, which is the pub noise, and that's played from one or more source speakers and recording, again, using the calibrated reference mic at the mouth reference point. Next, we do another ambient recording using the DUT microphone, and then the signal and noise acquisitions are repeated using the DUT mic to yield the signal input, which is the speech, and the noise input, which is the pub noise. Once we've done all of that acquisition and analysis, we do some post-processing where first we calculate the signal gain by subtracting the signal input from the signal output. And then we calculate the noise gain by subtracting the noise input from the noise output. And then finally, the signal to noise spectrum is calculated by subtracting the noise gain from the signal gain. And the reason that we're measuring the ambient noise in the room with both microphones is that for the best accuracy, the signal and the noise spectra should be at least 5 dB above the ambient noise floor of the measurement environment. Okay, so it's time to flip back over to SoundCheck. So when we open our sequence, we get our sequence node here. It's a standard sequence available on the Listen website. Gives us a brief introduction describing what the sequence does, shows us the final display, talks about the different software requirements. This does require RTA module and wave file equalization and a bunch of different hardware, either a head and torso simulator or a mouth simulator. We'll need a reference mic and some amplification for the noise speakers, as well as for the mouth simulator. We talked through the calibration and the hardware and the setup, and here's just a basic diagram of what I have next to me. In essence, is the hats, a couple of powered speakers, a reference microphone, and another amplifier to power the mouth. Okay, so let's run the sequence now. During the sequence run, there'll be a couple of sections where we're just recording ambient noise, so you'll hear nothing but silence for about 13, 14 seconds. And you'll also hear the speech played back twice, once for the reference mic, once for the DUT mic, and the same with the noise playback. That will also occur twice.
shelves were bare of both jam or crackers. A joy to every child is the swan boat.
The stems of the tall glasses cracked and broke. The wall phone rang loud and often.
The DUT mic is already in position, so we'll just press enter to continue.
The shelves were bare of both jam or crackers. A joy to every child is the swan boat.
The stems of the tall glasses cracked and broke. The wall phone rang loud and often.
Okay, so let's take a quick look at the results. The first XY graph here is the signal output, and that's the ambient noise here in purple that was recorded with the reference mic. Then we have the noise output here, and then the signal or speech output here. The second XY graph is the signal input that was recorded by the DUT mic. And again, from working from the bottom up, we have the ambient noise recorded by the DUT microphone here. We have the noise input here and the signal or the speech here. And so in the end, we wind up with this curve, which is the signal to noise spectrum that tells us exactly, how much, it shows us the ability of this microphone to reject noise at different frequencies. So down around 100 hertz, based on all the calculations, is able to reject about 12 dB of noise, and that attenuation gradually decreases as the frequencies increase it. But even up around 2K, there's still a bit of attenuation going on. So generally, this is a pretty good microphone, not great, not horrible, and the results are pretty believable based on my experience with it. So there you have it, a quick look at how to measure microphone noise rejection. And again, this sequence is available on the Listen website for download. If you were with us for the Microphones Basics seminar last year, you'll recall that we covered MEMS mics in great detail about their construction and theory of operation and so forth. So we're not going to go over that again today, but just wanted to remind you, how quite small these devices are. We have a little image here of a MEMS microphone next to a United States coin, a quarter. So I did want to remind you of the two types of MEMS microphones. First off, the analog MEMS, which has a very straightforward interface to the host circuit. It includes its own amplifier stage, and it outputs a usable signal level with a very low output impedance. And then there's the digital MEMS, where the analog signal from the microphone capsule is converted to a PDM stream. And the advantages of PDM are the electrical noise immunity, the bit error tolerance, and it offers up quite a simple interface in the end. But the thing is, it requires a very specialized test interface. And the test interface needs to convert the 1-bit PDM output to a 24-bit 48 kilohertz PCM stream. And it should have a programmable clock so we can measure the performance of the MEMS mic relative to the sample rate. And it should also have a programmable power supply so we can measure the performance relative to the supply voltage. And it also should have a power supply rejection impairment generator to measure power supply rejection ratio, or PSRR. Now, our partner Portland Tool and Die offers a couple of different MEMS interfaces. There's the DCC 1448, which is used for R&D, and I actually have one here next to me on the desktop here. And there's also the PQC 3048, which is used for production line test. The DCC is much more full-featured as you would imagine a lab instrument would be, but the PQC has a lot of advantages in terms of cost and size, which make it perfect for the production line. So next I'm going to show you a MEMS microphone test sequence, and you can find this on the Listen website, and it's called Measuring Digital MEMS Microphones. And it's actually a suite of 3 different sequences. There are 2 microphone measurement sequences in the downloadable folder. One uses the microphone substitution method to measure the MEMS microphone, and the other uses the equalized source method. And the third sequence in this package is used to measure power supply rejection ratio performance. And here's a typical MEMS hardware configuration like we would use in a test like this. We have the DCC, we have our computer running SoundCheck, and instead of having a separate audio connect and SC amp interface, we are going to be using the Amp Connect ISC, which combines both the microphone power supply and the amplifier all built into one chassis. And then we have our source speaker here. We're using a Rule and Care artificial mouth. So what I'd like to do now is to demonstrate to you a couple of those MEMS example sequences that we were discussing earlier. And the first one is going to look pretty familiar to you because it's just going to measure the response and the sensitivity of a MEMS microphone. And in this case, I've got my DCC set up over here, and I've got my B&K anechoic box, and inside of the box I have mounted the MEMS microphone that we'll be testing today. And I've already equalized and calibrated the speaker inside of the box because that's the sequence that we're going to be demonstrating here today is the equalized speaker method. So let's press play and then we'll discuss the sequence and the results. So it's a pretty simple display. Up on top here we get the frequency response of the MEMS mic mounted in the box. We can see that our units are dB RE1FS, and then down below here we've aligned the frequency response to 0 dB at 1K and applied some limits to it. And in this case the sensitivity passes at -26 dBFS, and the response also fits inside of the upper and lower limits here. And the sequence itself is very straightforward. We set up our stimulus, we do a play and record acquisition. We do have a resample step in here because the data coming in from the DCC is at 48K, so we need to downsample that to the sample rate of the Amp Connect here at 44.1. Once we've resampled the recorded time waveform, we can do the analysis, and then there's a step to determine the sensitivity and a limit step for the sensitivity and a limit step for the response, and then everything gets pushed out here to the final display. So it's very straightforward, very similar to the analog equalized speaker method that we demonstrated in our last seminar. So the next sequence I want to demonstrate to you measures the power supply rejection of the microphone. And in this case, we're looking at power supply at 217 Hertz because GSM TDM is now often a greater concern, and these are issues that come up when we're using MEMS microphones in communication devices like mobile phones. So when I run this sequence, we're actually using the system custom step in here to send command line executables to the DCC to put it into different states. So the first custom step sets the generator to sine. The second step sets the frequency to 217 Hertz. The third step sets the level. The fourth step turns the generator on. And the fifth step turns the generator off. And in between the fourth and fifth step, we're actually doing a record-only acquisition. Well, then we'll take the recorded time waveform, acquire the spectrum through the analysis step here, and then we'll do a post-processing step on the spectrum where we'll get the average at 217 hertz, which we'll call power supply rejection, and then that will go through a single value limit step with an upper limit only. So when I run this sequence, you're going to see a few windows open and close as the system custom steps are being executed. And then when we get to the end, we'll talk about the results. Okay, so on the XY graph here is the spectrum that we've acquired, and we can see that there is an outstanding feature here at 217 hertz, and the level of the 217 hertz frequency was minus 81.7 dB down, and that passed our limit, which I believe is set at minus 80. So this is a really simple way to check the power supply rejection ratio of your MEMS microphone. And again, all of these sequences are available on the Listen website for you to download and run on your end. It's also worth mentioning that there are a few different ways that we can actually communicate with and control the DCC unit itself. You'll notice that on the front panel we have a touch screen here, and we can enter all of the parameters via the touch screen here. As we just saw in the sequence we just ran, there's also the ability to use the command lines in a sequence by running them from a system custom step. And lastly, the DCC also has its own configurable message step within SoundCheck. So any of the parameters that we can configure through the command line or through the front panel are also configurable through the message step. So we could put a step in the sequence and actually change the state of the device while the sequence is running. So we can change the state of the clock, the sample rate, the VP, the data in state, the coupling mode, the power supply state, the other VP level here, the PDM decimation rate, and whether or not the PSR generator is on or off, and then some of the parameters around that. Our next topic is microphone arrays. And why would you want to use a microphone array? Well, if you were a test and measurement guy like I am, you'd want to use a microphone array because it would improve your measurement accuracy under certain conditions, or it just might decrease your measurement time. And if you were designing consumer products, you might want to use a microphone array because it would improve the performance of your device, such as a mobile phone or a conferencing system or something like that, where the performance would be enhanced by the use of an array. So next I'm going to talk about a few common use cases for microphone arrays, and then we're going to look at a couple of those in a little greater detail. But first, back to test and measurement. I talked a little bit about microphone arrays, and one practical use for arrays are for sound power measurements. And there's two here that we can discuss briefly. There's a 6 microphone array for automotive test and measurement. And then we may use a hemispherical array to do some sort of industrial measurement on an appliance or some piece of machinery where we wanted to measure its sound power. A multi-microphone array can also be used for directional measurements of a loudspeaker. So if you were here for our last seminar, we demonstrated polar plotting using a turntable. But another method for doing this is actually to set up a large microphone array around the loudspeaker and we can make all of our measurements simultaneously rather than having to make one measurement at 0 degrees and then incrementally rotating around the arc to 360 degrees. So it's an alternative to polar plotting, and it's much faster because we're able to acquire all of our angles simultaneously. The only limitation here is your number of channels. So you really do need to have quite a large array for this, and SoundCheck can support up to 64 microphones. So that should cover most of these applications quite nicely. People use spherical arrays for spatial recordings or spatial measurements. And in consumer products, we may use 2 or more microphones to create a beam-forming array. And again, a practical use might be in a phone, a television, or some sort of conferencing system where beam-forming is required. So let's talk a little bit about sound power. And there's an automotive application I want to talk a little bit about. And this comes from a paper that was written by Geddes and Blind back in the mid-1980s. And the paper's called Localized Sound Power Method. And in it, the authors propose that a single-point microphone measurement lacks sufficient stability to be useful for sound system equalization. And they went on to do a series of experiments looking at microphone arrays, starting with a large number of microphones. I believe they started with 18. And in the end, they found that they could get pretty good accuracy using a 6-microphone array and using spatial averaging from the measurements that came from each microphone. And in the end, I believe they said that they had 90% confidence that this array could provide plus or minus half a dB of accuracy in a 3rd octave measurement inside of a vehicle cabin. And this is still in use today, all these years later. And actually, somewhere down here, I have an example of the type of holder that might be used for such an array. The microphones are spaced about 15 centimeters apart, and generally in the automotive cabin, the array would be located at the user's head position and oriented in approximately a 30-degree angle. And there's another image of one with some microphones actually mounted on it. And sound power in industrial applications, we might have a hemispherical array around the device that we're testing. There is an example sequence in SoundCheck in the how-to examples folder in your sequences folder, and it's called power averaging. So it'll give you a good idea of how you can do this type of measurement using SoundCheck. And here's just an example of what a hemispherical array might look like, a series of microphones that would surround whatever our device under test is. So let's talk a little bit about beam forming. So MEMS mics are very attractive for their size, their affordability, and their low power consumption. And MEMS mics are omnidirectional, and that pattern is useful for many applications. But if directional characteristics are desired, then we can start using multiple MEMS mics for beam forming arrays. And we might include signal processing, such as delay, amplification, and filtering. And these can be applied to the MEMS microphone outputs to boost the desired signal and to attenuate unwanted noise. The thing with beamforming microphones is that they must be closely matched in both sensitivity and frequency response. And MEMS manufacturers tend to do a pretty good job of achieving both of these goals. So if you're buying a MEMS mic from a reputable, well-known manufacturer, chances are that they're going to satisfy both of these requirements. So next we're going to talk about a few different common types of microphone arrays. And the first one is the broadside array. And we typically find these used in televisions or computer monitors where the sound source is expected to be out in front of the device. Broadside arrays use 2 or more microphones, and they're all mounted along the same axis, and they're oriented perpendicular to the expected source of the sound. And by summing the outputs of the microphones, we'll greatly amplify the signals coming from the expected source, since they're all going to arrive simultaneously. And the sounds coming from the left and right of the array, well, those are going to have different arrival times, and therefore it's going to result in a smaller sum. So the sound of interest from the expected source is going to be amplified in the broadside array. Now, signals coming from directly behind, above, or below the array are going to have the same response as sounds coming from the expected source. And here's a little diagram of a simple broadside array. We have our sound source, we have our two microphones, and their outputs are summed and then sent out as an electrical signal. Next, we'll talk about the end fire array, and these are typically used when greater directionality is a requirement. The axis of the microphones is aligned with the direction of the expected sound source, and the sound arrives at the second or subsequent microphones after some amount of delay due to their different distance from the source. And the response of the first microphone is summed with the delay compensated responses of the additional microphones. And the on-axis sounds are summed to a much greater degree than the off-axis sounds, and that provides better attenuations of sounds coming from the sides and the rear of the broadside array. These are typically used in handheld devices that are pointed towards the sound source. And here's a little schematic of a simple beamforming end fire array where we have the sound source here, and then we have two mics that are different distances from the source but on the axis of the source, and then we have some delay compensation here, and then the electrical signal goes out after the delay compensation and the two microphone signals are summed. And lastly, we are going to talk a little bit about a microphone array that's used for localization. It's used to locate sounds which may be coming from different directions. And in this case, the microphones are located on the perimeter of a circle or of a sphere, and the time differences of the microphone responses is used to calculate the location of the origin of the sound. And a very common application here is something that's used by military and law enforcement to locate the source of gunfire. And here's the schematic of a localization array. So we have 4 microphones around the periphery of a circle. We have the sound coming from one source, and then we have some DSP where all of the microphone signals are going in here. The DSP is determining which one is closest to the sound, and that's how we're doing the localization here. So before I switch over to SoundCheck and do a brief demo of measuring a microphone array, I wanted to talk a little bit about the A to B automotive audio bus, because that's actually what we're going to be using for this demonstration. So we're going to kind of kill 2 birds with 1 stone here. We're going to measure a mic array. We're going to show you A to B. And inside of these microphone arrays over here, we actually have some MEMS mics. So we got a lot of stuff going on here. But a quick introduction to A to B, if you're not that familiar with it. It's a high bandwidth bidirectional digital audio bus, and it distributes audio, control data, and power over a single low-cost twisted pair cable inside your vehicle. So it has a lot of advantages, and I think one of the big ones is that it takes a lot of weight out of the vehicle, and it also can reduce a lot of cost. It supports I2S, TDM, PDM data streams, and also I2C control information. And it supports multiple sample rates and data transfer up to 50 MIPS. So it's a very versatile, flexible, and powerful system. Today we're going to be using the Mentor A to B interface, and it presents itself as an ASIO device inside of SoundCheck, making it easy to configure in the SoundCheck hardware. Here's a picture of the A to B analyzer, and here's a little bit of a schematic showing how one might set this up with your SoundCheck PC, the analyzer, and several slaves. Right now I've got a couple of slaves here, and each one is going to present themselves as a left-right pair, so we're actually going to be doing 4 independent channels of acquisition when we run our SoundCheck sequence. And then on the output side, this is showing an audio interface and a powered loudspeaker. In this case, we've got our old friend Amp Connect ISC here and a passive loudspeaker. I've already calibrated our little monitor speaker here that's sitting out in front of the rays, so we're all set with that. So at this point, I'm going to bring up SoundCheck, and I'm going to pop open the hardware settings. And as we can see up here on the input side, we have 4 channels. Let me get these channels arranged a little more cleanly here. We have the 4 A to B ASIO channels here. We have 2 microarrays, so we have S0 and S1. Those are our sinks, and each one has a left-right component. And we have set these up as digital devices with a 44.1 sample rate and 32-bit depth. And each one of these hardware channels here, the digital channels for the A to B microphones, has a corresponding signal path over in calibration. So I'm going to bring up the Mentor control panel here. I'm going to connect to the analyzer. That was successful. And then I'm going to start the system up with discovery. It's discovered 2 nodes. These are my 2 nodes right here. So that tells me that we're good to go with SoundCheck. Everything's up and running. So before we run our demo sequence today, I just wanted to open up the sequence editor and show you a little bit about what's going on in the sequence. And let me open up the memory list too, because I'm going to want to refer to that as well. So it's a very simple sequence in terms of the number of steps. It's just stimulus acquisition, 1 post-processing step, 1 analysis step, and a display. But we are doing some interesting things here that show off the power of SoundCheck, particularly under measurement conditions like this, where we have multiple input sources. So we start out with our stimulus file. It's a simple sweep from 10K down to 100 hertz with 12th octave resolution, and we're applying equalization to our source speaker that's here in the Brüel & Kjær anechoic box. Now here's what things get interesting in the acquisition step. And as you can see, I've got my 4 signal paths set up for the A to B microarrays that I have over here. And I'm giving them custom names. We're going to call them RTW, nice and short. And I'm also going to append the signal path names to the waveform names. And we can clearly see that over here in the memory list. And what I've done, I've taken the 4 waveforms that are going to come out of this acquisition step, and I've placed them in a group. And the reason I've done that is because now I can take all 4 of these waveforms and batch process them through our frequency shift step. And the reason we're frequency shifting here is because we're using 1 device for playback and 1 device for recording, the Amp Connect and the A to B analyzer. And even though they're both operating at 44.1 kilohertz sample rate, there's a possibility that they have slightly different clock rates. And the frequency shift step is going to correct for any slight discrepancies between clocks between the 2 devices. So I can put all 4 of these waveforms into a group, point to them as operand A, tell the step to automatically calculate their sample rate, and then I'm going to use the stimulus waveform as the reference waveform. So now we can process all 4 of these waveforms in a single step. And once again, the output from the frequency shift step, I'm going to take those 4 waveforms, place them into a group so we can do batch analysis. And that's what's going to happen over here. On the Waveforms tab, I have a custom group. I've got my 4 frequency shifted waveforms. And when the step is applied, we'll get analysis of all 4. And once that's done, we'll simply put the results up on 2 displays. And there we have our final display. one of these comes out very well matched, while the other one seems to have a little bit of a mismatch through the midband here. It could have something to do with this setup here. It's not really the best configuration for a good microphone measurement, but I wanted to have all of the equipment out in the open here, so certainly some reflections, and we're probably seeing it down here on this bottom XY graph. But the top ones look like they're pretty well matched. We can see that there's a little bit of a rising response up in the top end, and the second channel kind of shares the same, the second microphone pair shares the same type shape, but microphone number 2 just isn't quite in sync with microphone number 1 for whatever reason. So our next topic for discussion is intermodulation, or IM distortion. Microphone distortion is very difficult to measure. Using the standard methods that we've shown you here in these seminars, the source speaker itself is likely to have higher distortion than the microphone under test. So what can we do when we can't make traditional THD measurements on a microphone? There's an alternative, and that's using intermodulation distortion measurements. So for the example that we're going to discuss today, intermodulation uses a master tone, which in this case is a fixed tone at 100 hertz, and a slave tone, which is a sweep from 10 kilohertz to 224 hertz. And the two tones are played back at a 4:1 ratio. It's also very important that separate speakers are used for the playback of the stimulus here. So for example, we'll play the master tone through a subwoofer, and the slave tone, the sweep, would be played through a full range speaker. Otherwise, if we played this through a single source, the speaker would produce intermodulation distortion of its own. So very important that we use two discrete speakers for the playback here. And we have a sequence for this on the Listen website. It's called Intermodulation Distortion Sequence. So you can feel free to head over to the website and download that after our presentation today. And just a heads up that we're going to have a future seminar on distortion where it's going to cover a whole bunch of different distortion methods in much greater detail. So we won't do a demonstration of this today, but I will show you just a brief schematic of a setup that could be used for this type of measurement. We have our SoundCheck PC. We have an amplifier to power our full range speaker. We have an Audio Connect interface, and this assumes a powered subwoofer, so we have a line output to the powered subwoofer. We have a line out to the SC amp powering the full range speaker, and then we have our microphone under test out here in front of the speaker array. And the example that we show in our sequence note has a final display that looks like this, where we have the fundamental of the microphone under test at the top here. We have the IM2 and IM3 components shown on the display, and then down here on a separate XY graph, we have the total IMD. So once again, this sequence is available on our website, and there's actually a nice link in the sequence note that accompanies this sequence to a paper that Steve Temmie wrote back when he was working at Brüel & Kjær on distortion measurements, and there's a lot of great stuff in there. So feel free to check that paper out as well. So before we wrap things up today, I wanted to answer a couple of questions that came in on the survey forms from our past seminars. And the first question is pretty common, and it's how can I apply a weighting to a noise floor spectrum? And that's something you might commonly want to do when you're measuring microphone noise, input noise, things like that. And the thing is, there isn't necessarily an A weighting post-processing step in SoundCheck, but there's a very, very easy way to do it. And I wrote a small example sequence here to show you just how to do it. So let's open up the sequence editor and take a look at what's going on. So the first thing that we're required to do is actually recall an A weighting curve into the memory list. And we do that with this recall step here. And there is a DAT file in your SoundCheck data folder called A, B, and C weightings.dat. And when you point to that, you'll see that there are indeed 3 weighting curves in here. And today we're only interested in the A weighting curve. So we're going to highlight that and not select the other 2. And that way we don't clutter up our memory list with unwanted curves. So we'll just recall the A weighting curve. And aside from that, it's very straightforward. We're going to do a brief record-only step. We're going to do a spectrum analysis of the recorded time waveform of that record-only step, which is just recording the noise floor of our direct input. We have a shorting resistor on the input here. And once we have the spectrum, here's where we do the actual A weighting. So we'll use a arithmetic step where we're doing linear multiplication, and the spectrum's operand A, and the weighting curve is operand B, and I put a custom name down here for spectrum A weighted. So that's all you really need to do. Once you have your spectrum of interest, you just do some arithmetic on it, multiply the spectrum by the weighting curve using a linear multiplication operation. So let's just run the sequence and we'll see what comes out. And that's what we would expect. We have our unweighted spectrum here in blue, and then with the A weighting applied, we come up with this orange curve. And there's one more question I want to get to today, and that is, can SoundCheck measure microphone phase and polarity? And the answer is yes, it can absolutely do that, and we'll show that to you now. So what I'm going to do is I'm going to open up the standard microphone sequence. This is the one where we use calibrated and equalized source speaker. Everything's all set up in the Brüel & Kjær box here. It's already been equalized. And I'm going to run the sequence one time. So this will probably look familiar to you if you've been with us for some of our past seminars. Up here we have our microphone fundamental response, and then down below it's the fundamental that's been aligned to 0 dB at 1K. So let's talk about the phase first. And the thing is, in SoundCheck, phase is always available. It's just hidden from view. And if you want to look at the phase on an XY graph, you right-click on the graph, and there's an option down here to view the phase. So there's the phase response of our measurement. If we want to, we can go in and hide the magnitude and just show the phase here, or bring the magnitude back. So that's very simple to do. So there's phase, and the other question was about polarity. And the easiest way to go about this is to go into your analysis step, and on the delay tab, there's a checkbox here for polarity. And this is a simple polarity method. And what it's going to do, it's going to return a single value to the memory list. It will return a 1 if the polarity is positive, and it will return a -1 if the polarity is negative. So it's very easy to set a single value limit on the polarity value. So I'm going to click Apply here and go over to my Values tab, and now I can see that I have a value for polarity. And in this case, we're mostly concerned with the Y value here. It's a 1. That tells us that the polarity of the microphone is positive. So now we can add a limit step to our sequence. Have the limits group open. I'll go single value, lower only, and I'll stick that here. Point to my polarity value, and I'll set my lower limit as 0. So if it's 1, the step will pass. If it was -1, it would fail. So now I've got a new result in the memory list here. And actually, let's give that a name. More specific. And there's polarity. Drag it over here. And there we have our third result. So as you can see, it's very easy to measure phase. It's always there. It's usually hidden. If you want it just to review, come in and right-click on the plot area and select phase. And then the polarity value can be output by your analysis step. So hope that answers a couple questions for you out there. And that's it for the past Q&A. So this concludes today's presentation and our series on microphone measurements. So thanks again for joining us, and I'll see you all next time.